All right, we'll get started. So here we go. Welcome to our second recitation of the day. So here's my plan for today's recitation. I want to start off by doing some application problems with both the chain rule and with directional derivatives, so we can kind of see what these things exactly are, what they mean, and why we care about them. And then I'm going to do some more geometric problems involving tangent planes and normal lines and things like that to try to, get a better sense of what they actually mean and what they look like and things like that. So there's someone who's just signed in. So before I get started with any of that, are there any requests? Are there any requests that the folks here might have before doing anything? And since there don't appear to be any requests, we'll keep going. So to start us off, these are mostly problems that are coming from Stuart. So to start us off, let's consider as our first example. We've got the temperature on a surface. And this temperature is at some position x, y, and that's given by T of x and y. And we've got a bug. That bug is crawling on the surface. And the path that this bug is taking is given in parametric equations by x equals root 1 plus t, and y is equal to 2 plus 2 plus 1/3 t. So the question is, and we're also told that t sub x, 2, 3, we're told that this is equal to 4, and t sub y at 2, 3, the rate of change in those particular directions is 3. So the question is how much is the bug's temperature increasing or decreasing? So to answer this question, we need to remember what the chain rule says. Here we've got temperature, and temperature depends on two variables, x and y. It's the temperature at that particular point. But each of x and y depend on t. So this is just a simple application of what we sometimes call chain rule 1. The basic idea here is that the rate of change in the temperature at time. Oh, I forgot to include an important parameter in the problem. How much is the temperature increasing or decreasing at t equals 3 seconds? Forgot that important aspect. So, and that's important because that tells us that what we're really looking for is the rate of temperature change with respect to time at t equals 3. That's what we're looking for. And to answer that question, we need to look at del t, del x, dx dt, that's the chain rule, plus del t, del y, dy dt. And specifically, this all is happening at t equals 3. So, now by the way, at t equals 3, we also need to know what x is. X is root 1 plus 3, or in other words, 2. And y equals 2 plus 3 over 3, or in other words, 3. Now you see, by the way, why we really care about tx 2, 3 and ty 2, 3. Those are important pieces of data for us, because that tells us that what we're really interested in is del t, del x at 2, 3, and that's 4, del t del y at 2, 3 meanwhile is 3. Now what about dt, and what about dx dt? Well, dx dt is 1 over 2 root 1 plus 3, 1 plus t, just after taking the derivative, which comes out to dx dt at t equals 3. Actually, let me be a little more specific there and say this is at t equals 3, which in this case is 1 over 4, and dy dt is just the constant function 1/3. So the upshot of all of this is that after seeing all of this play out, we know now that dt, d big T, d little t, after 3 seconds, dt dx is 4 times dx dt at t equals 3 is 1/4, plus del t del y is 3, dy dt is 1/3, or in other words, 2. So the answer to the first problem is just 2. So what does that tell us? Let me actually be a little more specific, and I'll say that's 2 degrees Celsius, perhaps, per second that this insect or this bug is experiencing in change. It's rising by 2 degrees per second. Okay. So, which is a rapidly increasing. Maybe I should have chosen Fahrenheit. That plate is getting very hot, very fast. So, moving along, if there aren't any questions on that example, I think we're okay. I want to do a different example, again involving the chain rule. So suppose that we've got wheat production. So wheat production depends on, and let's say the wheat production is being given in pounds. And that depends on average rainfall and also on average temperature. So in other words, what that means is that the wheat production, which I'm calling W, is some function of rainfall and temperature. So R equals rainfall, which is in centimeters, and T is temperature, which we'll say is in degrees Celsius. Now let's say that we know that scientists find that the average temperature is rising at 0.15 degrees Celsius per year, and the average rainfall is decreasing at 0.1 centimeters per year. Now, furthermore, we also model. So we also further estimate that the partial derivative of wheat production with respect to the temperature is given by -2 pounds per degree Celsius, and the average wheat production changing with rainfall is 8 pounds per centimeter. So the question is, so 2 questions. First of all, what do these partial derivatives mean? And the second question is, what is dw dt? What is the average, how is wheat production changing with time in this model? So what do these derivatives actually mean? Well, del W del T is -2 pounds per degree Celsius. So the answer to the first guy, the answer to this first problem, is that wheat production wheat production declines by 2 pounds per a degree in Celsius temperature change, and increases by 8 pounds per centimeter of rainfall. Which makes sense if you think about it. If it gets hotter out, then the plants aren't going to do as well. But if there's more rain, they're going to do better. So this makes a certain amount of sense in terms of how you expect the production of your crop to change with different changes in your environment. What about dW dt? Well, again, oops, wrong letter. Again, this is a chain rule problem. And so that's going to depend on your change in temperature over time, but it's also going to depend on your change in rainfall over time. For those of you who like the tree diagrams, just to remind everyone what is actually going on here, we've got our wheat production, which depends on temperature and rainfall, and the temperature and rainfall each depend on time. As time goes forward, the average annual rainfall and the average annual temperature are changing. Now, what these tell us, in this case, del W del T, we're told is -2 times now dt dt. That's the amount of change in temperature per year, which we're saying is 0.15, because it's increasing at 0.15 degrees Celsius per year, plus 8 for del W del R, times, now the average rainfall is decreasing. The average rainfall, we're told, is decreasing at 0.1 centimeters per year, so it's times -0.1. So this becomes -0.3 minus 0.8, which in other words is -1.1 pounds per year. So what we're seeing in this case is how this crop production is changing with time if we're told something about how its environmental conditions are changing with time. This is one of the major applications of the chain rule, and how a lot of climate scientists, for example, explore what the long-term effects of climate change would be on our environment, and how we care about these kinds of things. The chain rule often comes into play with those kinds of analyses. Although, for the record, I don't actually think that that temperature is increasing quite at that level. It's alarming enough as it is, but 0.15 degrees Celsius per year. Good night. So that's what I want us to look at. So what are some other? So that's the chain rule. That's basically what the chain rule is telling us, and it's showing us how, what these different kinds of effects are. Stuart's got a lot of really good problems with the chain rule, and a lot of application problems in the back of that section. So section 12.4, I believe. No, 12.5. Not 12.5. What am I saying? 14.5. So in 14.5 is the chain rule section. Stuart's got a lot of good application problems on that, so you can sort of get a better sense of what these things mean. Let's look at directional derivatives for a little bit. What are some examples that, that we can look at here. So here's one. So, so this is directional derivative. So near a buoy, the depth of the lake at some point with coordinates x, y is defined by the equation z is the depth, which is 200 plus 0.02 x squared minus 0.001 y cubed, where x, y, and z are all measured in meters. And we've got a fisherman. And the fisherman starts at the point 80, 60, and moves towards the buoy. And for reference, let's say that the buoy is at the origin. So the question is the water getting deeper or shallower? Now we need to ask ourselves, what is this question actually asking? What it's asking is, how is the depth changing? It's asking how the depth of this lake is changing. And not only that, not only is it asking how the depth of the lake is changing, but it's asking how the depth of the lake is changing in a particular direction. So we're given a direction and we want to know how much this depth is changing, which means we're going to need to, it's not just because I said so, we're going to need the rate of change of the depth in a specific direction. I.e., that means you're going to need the directional derivative, du f, at the point 80, 60. And that, by the way, is it's the same thing that we saw before. The gradient at this point 80, 60, dotted with u. Now, in this case, I'm saying that f, x, y, that's going to be our depth. That's our depth function. And that is going to be the same function as before, 200 plus 0.02 x minus 0.001 y cubed, x squared, excuse me. Which means that we need to know the gradient and we need to know what this mysterious vector u is. So let's start with the gradient. So what is the actual gradient in this case? And let me just be a little more general, and I'll say specifically I wondered about just the general gradient at some point in the lake. What is the gradient vector? Tell me what the gradient vector is. So the gradient is going to be, in this case, 0.04x minus 0.003, x. In the x direction, the negative 0.003 y squared in the y direction. That's the gradient of this function, which means in particular that if we take the gradient at the point 80, 60, that is going to be 0.32. 3.2, excuse me, because it's times 6, or times 10. So 3.2, comma, And then the next one is 60 squared is 3,600. And 36 times 3 is 108 times 100 minus 100 again. So the that's going to come out to 10.8, I believe. So, or negative 10.8 rather. So that's negative 10.8. So that's our gradient. And so we've got our gradient, and now we need to find out what u is. Now u that's the same direction as negative 80 comma negative 60. That much we know. But that's the same thing as the direction negative 4, negative 3. After just factoring out a factor of 20. And the magnitude of that thing, so let's say that we're going in the direction of v, which is negative 4, negative 3. Well, then the magnitude of v is root 16 plus 9, or in other words, 5. So our vector u, in this case that we're interested in, is 1/5 times negative 4, negative 3. So what that means is that our directional derivative that we're actually interested in is du f 80, 60, which in this case is going to be 3.2 negative 10.8 times 1/5 negative 4 negative 3. And if you do the calculations for a second, that's going to come out to 1/5 times negative 12.8 plus 32.4. And after dividing by 5, that comes out to 3.92. So that's our final answer. So the question, why are both numbers in the original u vector negative? So what we have to remember here is, let's say that we're working, I'm going to try to find a, so what space haven't I used yet? So if we're thinking about our workspace here, you've got your lake, you've got your x direction and your y direction, and and the fisherman is starting out over here. I'm calling this 80 and this 60. And what we're told is that he's going towards the buoy. He's going towards the origin. So you're starting here, you're going towards the origin. The fact that we're going towards the origin means that we're actually going in, the vector is pointing in the opposite direction from where we currently are, because we're going towards the center of this space. Does that make sense? Yeah, sure, no problem. So so now the original question is this water getting deeper or is it getting shallower? So what do we think? Given that we just found that their directional derivative is 3.92, what does that mean for our lake? Is it getting deeper or is it getting shallower? It's actually getting deeper in this case. So in other words, so the fact that the depth is increasing, which means that we're getting deeper as this fisherman is going towards the buoy. Since this is a positive number. So the depth is increasing. Okay. So let's do another thing like this. So similar issue here. So the temperature in a metal ball this is inversely proportional to the distance from the center. And let's suppose that the distance from the center is the origin 0, 0, 0. And we're also told that the temperature at the point 1, 2, 2 is 120 degrees Celsius. So there are two questions here. First of all, find the temperature towards the point. Find the temperature at the point. I'm writing all of this wrong. Excuse me. Let me try that one more time. Find the rate of change at the point 1, 2, 2. Towards the point 2, 1, 3. And the second problem is find the direction of greatest increase. At any point. So again, rate of change at a particular point towards another point. So for A, once again, we need to use our directional derivative formula, gradient of t dotted with u. Now we don't know what t is in this case. All we know is that t x, y, z is inversely proportional to the distance. What that means is it's some constant k over square root of x squared plus y squared plus z squared. That comes from the fact that we're working with something that's inversely proportional to distance from the center. Now I don't know what k is. I do know that t of 1, 2, 2, well, that would be k over root 1 plus 4 plus 4, or in other words, k over 3, and that's 120, which tells us that k is actually 360. So now we know what our actual temperature function is. That's good. That's very helpful. We can take it a step further now and say, okay, well, if that's what our temperature function is, then we need to know what the gradient of t is. The gradient of t is what? Well, just taking the derivative with the chain rule as usual, or the Calc 1 chain rule in this case. This would come out to negative 360 x over x squared plus y squared plus z squared to the 3 halves. Negative 360 y over x squared plus y squared plus z squared to the 3 halves. And negative 360 z over x squared plus y squared plus z squared to the 3 halves. In particular, that means that the gradient of t at the point at the point 1, 2, 2 would be negative 360 over magnitude cubed, which in this case would be over root 1 plus 4 plus 4 cubed, or 27 in other words, times 1, 2, 2, the vector. Let me just re-express that a little bit. Negative 360 over 27, 1, 2, 2. Dividing those both by 9, that becomes negative 40 over 3. So now we need to know what the vector is, that the direction we're going in. So u now it's very tempting to say that u is going in the direction of 2, 1, 3, right? We're told that we've got the point 2, 1, 3, and it's very tempting to say that it's going in that direction, but that's not right. Let me just make this really clear. So I haven't quite finished my thought yet, but you know what? I'll mention this when I'm done with this. It's the same direction as v, which I'm calling. So you're going towards the point 2, 1, 3. So it's 2, 2, 1, 3 minus 1, 2, 2. Or in other words, 1, negative 1, 1. So the upshot of that is that u is root 3 over 3, 1, negative 1, 1. Not in particular, so it is not the case. So do not do this. It is not the case that we've got our vector is 2, 1, 3. That's not true. And the reason that's not true is because 2, 1, 3 is just a point that we're going toward. It's not a direction in and of itself. It's just a point that we're walking towards. But that's not the same thing as saying it's a direction. And if you try drawing it out, maybe you can see why, if we're thinking about the actual direction that we're going in. It's a common mistake, but don't make it. Going on to a new slide. It's the same problem, just new slide because I've run out of space. So just to recap, we've got that u is 1 over root 3, or I guess to be consistent, root 3 over 3, times 1, negative 1, 1. And the gradient at our point 1, 2, 2, we said was negative 40 over, was negative 40 over 3 times 1, 2. I don't know why I said 12 there. 1, 2, 2. Let me just make sure that I got those correctly from what I wrote down before. And yes, I did. Good. So our rate of change is the dot product of these things. So that would be negative 40 root 3 over 9. 1, negative 1, just multiplying the constants out front. 1, negative 1, 1, dotted with 1, 2, 2. That's going to come out to negative 40 root 3 over 9 times 1 minus 2 plus 2. Or in other words, just negative 40 root 3 over 9. So that's what the rate of temperature changes. And if you want to include units, I would imagine those units would be in degrees Celsius per meter. That's how much the temperature. So it's cooling down as we're going towards that point. Which actually makes a certain amount of sense because the point that we're interested in is 2, 1, 3, which has a magnitude of 4 plus 9 plus 1, so root 14, which is further away from the origin than our previous magnitude of 3. So, and that makes sense because if we're saying that the temperature is inversely proportional to the distance from the center, that means that the temperature is cooling down the further you get out. So the part B here is about finding the direction of greatest temperature increase at any point. So for part B, recall that we found that the gradient of the temperature is negative 360 over root x squared plus y squared plus z squared times x, y, z. Now I'm going to draw this in 2 dimensions, even though it's a 3-dimensional problem, because I can't draw 3 dimensions very easily, and it's even worse when it's on a digital whiteboard. But basically what that means is if here's your point that you're interested in, x, y, z, the gradient is going towards the origin, right? It's in the opposite direction from where you were. So it's the same vector. It's the same vector in this case, just some negative constant. I don't know what that constant is, but times x, y, z. Negative c, some negative constant. The upshot of all of this is that this temperature increase, actually, it's happening in the opposite direction. So that's to say that the direction of the greatest temperature increase is towards the origin / towards the center, which shouldn't really be too much of a surprise. But it's nice to see actually there's a mathematical reason why it works out that way. Any questions? The last couple of problems I want to do basically involve this stuff with the hold on a second. Basically involve things like tangent planes, normal lines, and some more geometric questions. So bottom line, whenever we're finding tangent planes and normal lines, this should conjure up a fairly specific image in our minds. For tangent planes, the tangent plane is some plane that just barely skims the surface. It just barely skims the surface of what we're looking at and hits that particular point. And the normal line, meanwhile, is simply just the line that's orthogonal to that plane at that point. That's all that is that we're really looking at. So this is the image we should be thinking of whenever we're dealing with these kinds of problems. And if you just keep this image in your mind, this will make certain other things work out a lot more nicely. So and will help you remember how to go about doing these things. So the things to remember, the most important thing to remember is that the gradient of some function f(x,y,z) is orthogonal to level surfaces. And the other important issues are equations for lines and planes. And more specifically, you need two things. First of all, you need a point on whatever your line or your plane is. And you need either a vector in the direction or a vector parallel to either a vector parallel to the line or orthogonal or / normal, those are synonymous, to the plane. And if we think about this image, and if we're thinking about what the gradient is, it's clear, I think it's relatively clear after staring at this for a second, that this vector that we want, I'll make this green and bold, that vector that we want is the gradient of f, right? That's just the gradient of our vector. Because if we're working with something that's parallel to the orthogonal line, and the gradient is orthogonal to the surface, then the gradient should be the vector that we want. And likewise for the tangent plane. So that's the most important thing to just keep in mind here as we're going about this. So let's say, for example, we want to look at the surface x equals y squared plus z squared plus 1 at the point 3, 1, negative 1. Oh, sorry. 3, 1, negative 1. Well, what you can do is you can re-express this as, trying to find the tangent plane and normal line. That becomes x minus y squared minus z squared equals 1. So we can just let f x, y, z equal x minus y squared minus z squared. We have to find the vector. We have to find the gradient, the normal vector. So the point that we need, the point for these both is going to be 3, 1, negative 1. The normal vector, or the gradient, is the gradient of f, which is 1, negative 2y, negative 2z. So the gradient of f at the point 3, 1, negative 1 is going to be 1, negative 2, 2. That's about it. So now we're basically there. We can say in this case that the tangent plane is x minus 3 minus 2 y minus 1 plus 2 z plus 1 equals 0. The normal line has parametric equations. X equals 3 plus t, y equals 1 minus 2t, z equals negative 1 plus 2t. That's about it. That's really almost all there really is to it. Let's do another example just so we can see this in action one more time. Let's suppose that we want to look at the equation, or we'll look at the surface defined by, I don't know, let's say x to the 4th plus y to the 4th plus z to the 4th equals 3x squared y squared z squared. So we want to find the tangent plane of the normal line. We're going to find these things at the point 1, 1, 1. Well, again, this comes down to understanding what we need. We need a point which we've basically been given. That can just be the point 1, 1, 1. And we also need a normal slash direction vector. I can't spell the word direction, apparently. And for that, we're just going to use the gradient. But what's f? f x, y, z is going to be everything in the equation that involves variables. So here, we're going to take that to be x to the fourth plus y to the fourth plus z to the fourth minus 3x squared y squared z squared equals 0. And if you take that gradient, just go off and calculate it directly. I'll give people watching this a second to pause and then try doing this on your own before I tell you what it is. But this comes out to 4x cubed minus 6x y squared z squared. 4y cubed minus 6x squared y z squared. 4z cubed minus 6 x squared y squared z. So if you actually plug in the point 1, 1, 1, what does that become? 4 minus 6, 4 minus 6, 4 minus 6, or in other words, negative 2, negative 2, negative 2. Now, by the way, what we care about is this gradient, but you don't really have to use that vector exactly. You just need a vector that's parallel to it. So in other words, we can use the vector v equals negative 2, negative 2, negative 2. That's the gradient. Or we can use the parallel vector that's given by 1, 1, 1. That's parallel to the vector negative 2, negative 2, negative 2. They're clearly scalar multiples of each other, after all. So the tangent plane and the normal line, we're basically ready to say what those are. Now, the tangent plane x minus 1 plus y minus 1 plus z minus 1 equals 0. Or in other words, x plus y plus z equals 3. Normal line, meanwhile, the normal line, meanwhile, would be given by almost the same exact thing. X equals t plus 1, y equals t plus 1, z equals t plus 1. That's about all there really is to it. Okay, I want to do a couple more just to sort of really see what some interesting kind of ways you can look at these geometric questions are. So here's another example. Here's the question. At what point does the normal line through one, 2, 1 of the ellipsoid ellipsoid given by 4x squared plus y squared plus 4z squared equals 12. So you've got this ellipsoid, you've got a normal line through it, and at what point does it intersect the surface x squared plus y squared plus z squared equals 102? So to answer this question, first of all, we need to find what the normal line is. And the direction vector is going to be given by the gradient of f at the point 1, 2, 1. And as usual, we say that f, x, y, z is 4x squared plus y squared plus 4z squared. So after we take the gradient of f is 8x, 2y, 8z. So you plug in the points 1, 2, 1 into that, f1, 2, 1 now becomes 8, 4, 8. And again, we can also use the parallel vector 2, 1, 2. Might make our lives a little bit easier to reduce this to a simpler vector. By the way, I am not claiming that 8, 4, 8 and 2, 1, 2 are actually equal as vectors. That is absolutely not what I'm claiming, because they're not. They're not the same vector. But they're parallel vectors, and the fact that they're parallel means that we can use either of them to answer the questions we're trying to address. So in other words, the normal line has the direction vector given by 2, 1, 2. And it's through the point 1, 2, 1. So the parametric equations are exactly what we're used to, 1 plus 2t for x, y equals 2 plus t, and z equals 1 plus 2t. Now the question is, when does that intersect this? Sphere? To answer that question, we need to know what the t value is where it intersects, and for that, all we have to do is just plug in these points into the sphere equation. The powerful thing about this is you just plug it into the equation, and that tells you where on the sphere this all is actually going to work out. So this gives us 1 plus 2t squared plus 2 plus t squared plus 1 plus 2t squared. You undo all of that, that becomes 1 plus 4t plus 4t squared plus 4 plus 4t plus t squared plus 1 plus 4t plus 4t squared. Combine all of that together, you get 9t squared plus 12t plus 3 is 102. I'm sorry, not plus 3, plus 6, excuse me. Now you can divide that equation by 3 to make our lives a little bit easier. This becomes 3t squared plus 4t plus, or rather, actually, let me do it this way. So plus 2. 102 divided by 3 is 34, I think. No, is that right? Yeah, that is right. 34. So you can re-express this by saying this is 3t squared plus 4t minus 32 equals 0. So as you're doing this, we now just need to work out what t is. And this, I think the best thing to do here is just to hit this with the quadratic formula. So in other words, that becomes -4 plus or minus the square root of 16 plus 4ac, 12 times 32 over 6 2a. Or in other words, you can factor out a 4 from the top. This becomes -4 plus or minus 4 times 1 plus 12 times 2, so 24 over 6. Or in other words, -4 plus or minus 4 times 5 is 20 over 6. And we're almost done. This, in other words, becomes either -4, or if it's positive 20, 20 minus 4 is 16, so either -4 or 8/3. So this normal line will intersect this, this sphere at 2 different points, where t is either -4 or 8/3. I need to do a new page again. So we've got x is equal to, I need to remind myself of everything, 1 plus 2t, y equals 2 plus t, z equals 1 plus 2t. And we just found that t is either -4 or 8/3. That allows us to find the two numbers that we want. So for t equals -4, well, it goes back into the original parametric equations for the normal line. X equals 1 minus 8 or -7. Y equals -2. Z equals -7 again. So this becomes the point -7, -2, -7. Or we could have t equals 8/3. T equals 8/3 would give us x equals 1 plus 16/3, or in other words, 19/3. Y equals 2 plus 8/3, or in other words, 14/3. And z again would be 19/3. So, which would give us 19/3, 14/3, 19/3. Oh, sorry, 19/3, not 19/13. A little overexcited with my keystrokes. Or writing, whatever the case may be. So here are the 2 points where the normal line intersects this sphere. Okay, I want to do one more problem. Let's do one more of these sort of geometric exploration kind of things. So here's the question: at what point on the surface x squared plus y squared plus 2z squared equals 1 is the tangent plane parallel to the plane x plus 2y plus z equals 1. The important thing to remember here is what it means for planes to be parallel. Parallel planes Well, if you've got parallel planes, all that means is that their normal vectors are parallel. So that tells us that the gradient of f has to be parallel to the vector 1, 2, 1. Now the gradient of f, in this case we're saying, as usual, fxyz is x squared plus y squared plus 2z squared. So its gradient is 2x, 2y, 4z. So what we want is for 2x to be equal to c 2y to be equal to 2c and 4z to be equal to c for some c. And why do we want that? Why does that have to be the case? Well, that's happening because what we really want is for these vectors to be parallel, and for the vectors to be parallel, they have to be scalar multiples. So 2x, 2y, 4z has to be equal to some constant c. Actually, let me clean that up a little bit. Is some constant c times 1, 2, 1, the normal vector for the plane that we were given in the beginning of the problem. Okay, well that tells us that that tells us a couple things. That tells us, for one thing, that that y equals c. So we've got 2x equals c, y equals c, and 4z equals c. So in other words, we know that 2x equals y, or in other words, y equals 1/2 x, and 4z equals, so 4z equals y as well, in equals 2x, which is to say that z equals, which is that z also equals 1/2 x. So what we're going to do is we're going to apply this to the original problem, to the original equation. The original equation for the ellipsoid, x squared plus y squared plus 2z squared, because we still have to think about that, because that point is going to be on this ellipsoid. And that's going to be x squared plus x squared over 4 plus x squared over 2 equals 1. You combine those things, though. 4 plus 2 is 6 plus 1 is 7. So that tells us really that 7/4 x squared equals 1. Yeah. So x is going to be, so that tells us that x is plus or minus 2 over root 7. Respectively, y is also going to be 1/2 x, so y is plus or minus 1 over root 7, and z is plus or minus 1 over root 7. So there are 2 points where this is going on, and we've just found those 2 points. Right. So are there questions for anything that we've done today? And if there are not any questions or further requests for things to do, then we'll end our session now. Thank you for tuning in, and I will post these slides to Canvas in a couple hours. Thank you.